Welcome to this video. In this video, we will be talking about vector and matrix norms. And by the end of this video, you will be able to calculate vector norms. You will be able to choose appropriate norms, and you will be able to calculate matrix norms. Okay, so what is a norm? Basically, a norm is a real number assigned to a vector or a matrix. The notation for a norm is just two vertical lines on either side of either the vector or the matrix. Now, norms have four distinct properties. The first one is that the norm, which is a real number, is always greater or equal to 0, so it can't be negative. And the norm of a matrix or a vector, here in this equation A can either be a vector or a matrix. So the norm of a vector or a matrix is only 0 if the entire matrix or the vector is equal to 0. The second property is, here we go, second property is that if alpha is a real number, then the norm of the product of alpha times A, the vector or the matrix, is equal to the absolute value of alpha multiplying the norm of the vector or the matrix, which means we can pull a real value out of the norm and just taking the absolute value and then doing the product with the norm of the vector or the matrix. Property number 3 is that if we take the norm of the product of two matrices or vectors, that result is smaller or equal to the product of the norms of the two entities. And finally, the fourth property is if we take the norm of the sum of two vectors or matrices, that norm will be smaller or equal to the sum of the norms, and that's the triangle inequality. So those are the four properties of norms, and let's apply them to vector norms and look at specific forms of these norms for vectors. The first one we're going to look at is the so-called infinity norm. So the infinity norm, indicated by a little infinity symbol at the subindex after the final two downward vertical lines, that is simply the largest absolute entry in the vector x. The second norm is the 1 norm. Now the 1 norm, indicated by the subindex 1 behind the norm symbol, is simply the sum of all the absolute values that are in the vector x. So you take the absolute value of all the entries and just sum them up, and the result is the 1 norm of this vector. And then finally, the Euclidean or the 2 norm, both the Euclidean and the 2 norm for a vector are exactly the same. They are the length of the vector x. If you remember, the length of, from linear algebra, right, the length of a vector is you sum up the squares of all the entries and then take the square root of that. That is the magnitude of the vector or the length of the vector. And in terms of norms, that is the Euclidean norm, or also called the 2 norm. Now, what can we use these norms for? What is their purpose? So let's say you solve a linear system, which means you not only have a single solution value, but you have very many solution values. Let's say, for example, if you had 10,000 equations that you're solving, your vector x will have 10,000 solution values. And now if I give you the task, tell me in a concise way how good is your numerical solution to this system of 10,000 equations, provided you would know the true solution. Well, if you know the true solution, right, you can calculate the true error or the true relative error, right? And you can do this for every one of these 10,000 numerical values, the 10,000 numerical solutions that you have for the 10,000 equations. Now, reporting all of these 10,000 error values is not really a concise way, right, of judging whether your result is good or not. You would want to boil those 10,000 values down to a single number. And that's exactly what a norm will let you do. It will boil down these 10,000 values into a single number and do this in a systematic way. Now we have these 3 or 4 different norms we can choose from. So which one of these norms should we use? Well, if you're interested in the largest individual error out of those 10,000 values, which is the worst result, which has the largest error, well, then you would use the infinity norm of the error vector. If you are interested in an average of the error, for example, an arithmetic average, then you would use the 1 norm, apply the 1 norm, and then you'd also have to divide by the number of entries to get to the arithmetic average. If you're interested in a root mean square type measure of the error, well, in that case, you would look at the length, you would look at the 2 norm or the Euclidean norm. So it really depends on what you are interested in, how you want to boil these numbers down, which one of these norms you would choose to calculate. Here's another example. Let's say you take a pressure measurement in a tank every 1 second for 24 hours. Just to say that you have an enormous amount of pressure values that you measure. Now, which of these norms would you use to check that the maximum pressure rating of the tank was not exceeded? Meaning that the largest pressure that you measured wasn't above the rated tank value. Well, you would use the infinity norm because that tells you the largest absolute value. What norm would you use if you wanted to check that the average pressure does not exceed the long-term storage pressure rating of the tank? Well, if it's an average pressure, right, you would use the 1 norm, right? And the 1 norm you would still have to get the actual average value. You would have to divide the result of the 1 norm by the number of measurements to get at the arithmetic average value. What norm would you use to check that the pressure fluctuations do not exceed the rating of the tank? Something with fluctuations, right? You would usually use the 2 or the Euclidean norm to do this. But in order to calculate this, you would take the 2 norm of the difference of the measured pressure and the mean pressure you can calculate using the 1 norm. So depending on what you want to know of a large vector of data, you would use the appropriately different norm. Okay, so that's vector norms. Now let's talk about matrix norms. Why do we need matrix norms? Well, in principle, we need matrix norms to help us calculate the corresponding vector norms if our vector is the solution of a system of linear equations. So if our system is built up with a matrix, we will need to be able to calculate matrix norms to find the vector norms of our solutions. Okay, so let's define the corresponding matrix norms like we did for vectors. Let's start with the infinity norm. So the infinity norm is basically the largest row sum of absolute values. So for each row of the matrix, you sum up all the entries in this row, the absolute values of those, and then you will take the largest one of these row sums, and that is the infinity norm. The 1 norm is similar. Instead of doing row sums, though, we will do column sums. So we do column sums and we take the largest one of these column sums, and that will be the 1 norm. The Euclidean norm is simply squaring every entry in the matrix, summing all of these entries up, and then taking the square root of this. That is the Euclidean norm. Now for matrices, the Euclidean norm and the 2 norm are 2 different things. The 2 norm for a matrix is defined as the largest eigenvalue of the matrix. And written in linear algebra terms, this is in the following manner. You take the largest value of x being an eigenvector of the 2 norm of a times x divided by the 2 norm of x. Right? A times x up there in the numerator, that's a vector, so we can take the 2 norm of that vector, and in the bottom we take the 2 norm of the eigenvector. You see the relationship here, a times x. If x is an eigenvector, that is lambda times x. So this would be the largest eigenvalue of the matrix A. Okay, so let's calculate the infinity norm for an example. So here is a matrix, and let's just, a 4x4 matrix, let's calculate the infinity norm of this matrix. So I'm just copying the matrix over here. The infinity norm was defined up here, so we take the sum over j, and j is the second index in the matrix here. So we go along a single row I and sum up the absolute values of each one of the entries in the row I. So let's start with the first row. So we're going to sum up every one of these entries' absolute value. So that would be 1 plus 3 plus 2 plus 1 absolute values. So that's 4, 6, that's equal to 7. Then we do the same thing for the second row. So we have 0 plus 2 plus 3 plus 1, 5 plus 1, that's equal to 6. And we do this for every row. The third row, it's 2 plus 1 plus 1 plus 0. The result is 4. And then the last row, it's 0 plus 1 plus 0 plus 2. The result is 3. So we've done the operations inside here of the statement for the definition of the infinity norm, what's basically the sum operations. And now we do this outer operator, which just says, well, take the largest one of these results. So we look at 7, 6, 4, 3, and we just take the largest one of those values, which means that the infinity norm of this matrix A is equal to 7. All right, thank you for watching.